Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, count increasing quadruplets. The problem states that you are given a array nums and you need to return the number of increasing quadruplets. Now, what is a quadruplet? What is an increasing quadruplet? A quadruplet ijkl is increasing if it satisfies these two conditions. I, j, k and l should be strictly increasing and nums of I should be less than nums of k which should be less than nums of j, which in turn should be less than nums of l. So if a quadruplet ijkl satisfies these two constraints, we will call that a increasing quadruplet and we need to return the number of such increasing quadruplet. Now let's take an example. In this example 1 3 2 4 5, one possible quadruplet is 0 1 2 3. Now 0 1 2 3 contains these four elements 1 3 2 and 4, and these four, first of all, this 0 1 2 3 satisfy these constraint, first constraint, which is I should be less than j, should be less than k, and which should be less than l. So it is 0 1 2 3, and hence this constraint is satisfied. Now for the second one, 1 which is less than 2, 2 is in turn less than 3, and 3 is in turn less than 4, and hence the second condition is also satisfied. So which implies that the quadruplet 0 1 2 3 is a increasing quadruplet, and there are only two possible quadruplet in this particular array, and hence the result is 2. Now hope the problem statement is clear. Now as always, I would like, the problem is bit involved, so instead of solving the original problem which includes I, j, k and l, let's try to solve a simplified version of the problem wherein we only have three indexes, right? I, j and k. Now if you haven't solved this kind of problem at all in past, I would encourage you to go a further one step down and solve this for two array indexes only. So again, before doing that, so here we need to find quadruplet, and we can do this easily in order n to the power 4, but n to the power 4 will not pass, right? And we need to come up with something which is less than order n to the power 4, right? The same constraint will apply to your reduced problem as well. In your reduced problem, which is with three indexes, we can easily solve this in order n cube, but we will try to solve this in less than order n cube, maybe in order n square or even less than that. So I would strongly encourage you to pause the video right away and give it a try. Now hope you have tried it. If not, I would again encourage you to try it, and let's see what the solution is. So we have three indexes I, j and k. We can simply fix these three indexes and get the answer in order n cube, but we have to do it better than order n cube. Now if we have to do better than order n cube, we can't fix three indexes, right? So let's try to fix two indexes only. So let's say we fix I and j. So we are iterating over all possible combination of I and j. Let's say this is one possible combination of I and j. Now for this I and j, we can't iterate over k. So what we need to find, what we need to ask for is, okay, given this I and j, tell me how many k's are possible. In other words, find me all the indexes after this j such that they are greater than 2. That's what this means in this particular context. Now, and we need to do that in order one time because we are iterating over I and j already. So order n square is already done, right? So we have to do that in order one time. Now, can we, okay, so first of all, like the pseudocode is something like this, right? So uh, we will be iterating over I and j, and for each I and j, we want to calculate how many uh, how many indexes are there which are greater than the value at j. So let's say we, like, first of all we need to find in order one time. So we have to do something like this, like there should be some array, we have calculated that array from before, and we are just addressing that array to get our final output. So now this is order n square, but we need to now ensure that can we calculate this calculate after as well in order n square or not. So what we need to calculate? We need to calculate, given a index j, find me all the indexes k which are after j and which are greater than the value of j. So in this particular problem, like for this, there will be two indexes, 4 and 5, because 4, these indexes come after j and their value is also greater than 2. Notice that 3 has a value of greater than 2 as well, but 3 comes before j. So the value of number of indexes for this particular j would be 2, and we will just add 2 in our result. So now only thing we need to calculate is how to do this in order, in less than order n square time, this calculate after. Now this is very easy. First of all, we can just iterate over all the indexes j and find out this as well. So what we can do is, we can simply iterate over all the index j. So this is, let's say this is j, and for each j we will iterate over all k, right? So for this particular j, k should be after this, right? So we iterate over all the indexes from I plus 1 to n, and whichever indexes are less than array of I, we will just include that in our result. So this entire thing runs in order n square time, and this entire thing also runs in order n square time. So we have solved this in order n square, right? So hope this is clear. Now we can easily reduce the time complexity of this function to order n log n. Currently it is n square, right? But we can easily reduce this to order n log n. But if we reduce this to order n log n, the overall complexity would stay still the same, because here we have order n square, right? So let's just assume that you have to do this in less than order n square as well, right? So again, I would encourage you to pause the video once again and try to think if you can solve this problem in order in less than order n square or not. Now, one thing again with the same concept, we if we have to do order n square, less than order n square, we can't iterate over two indexes I and j. We have to reduce this first, and if we reduce this first, we have to now iterate over only one index. Now, which index will you iterate over? So if you iterate over I, you need to know j and k as well. Now, once you, let's say you find out j with this exact same formula, for finding out k, you need to know j. So you can't actually find j, you can't actually find k in, in less than order n square time in that case. So in this kind of problem, it always makes sense to fix j. Now why j? Because if you fix j, you know you can do some kind of pre-computation and find out how many such pairs are there, and again you can do some kind of pre-computation and find out how many such pairs are there. So the latter part, which is how many pairs satisfy these constraint, is something we already know. Now if we can just calculate this part as well in order in less than order n square time, then we are done, right? So what will the pseudocode would look like? So let's just remove this for now, right? So pseudocode would look something like this. Now instead of two, we are now iterating over only one index, which is j. And similar to before, we have also calculated before smaller as well this time, right? So now we are saying that okay, for this j, tell me how many i's are there and tell me how many k's are there. Let's say there are two possible I, or in let's say this is j and there are two possible I. This I is, or there is one possible I, but there are two possible k. Let's say this k and this k. So how many total pairs are there with this j? Two. Like you will take this I with this k first, and then you will take this I with this k first. So you are basically multiplying these two numbers. So that's what we have done. We have just multiplied before smaller and after greater, right? So now our motive is to solve this and this in less than order n square time. And if we are able to do that, the entire complexity would be less than order n square. Now this part we already know that we can solve in less than order n square. This is just a sorting. You can just sort the array and just find out which elements, like just sort the array and just find out the, just take care of the indexes as well while sorting, and you will be done. And the same technique you can apply for calculate before as well, and you will be able to find it in less than order n square time. So that's the main idea behind solving these kind of problem, wherein you start with very brute force. We have started with order n square, then we saw that okay, we let's try to fix one less index and pre-compute something. So if that pre-computation is something we can do this in less than order n cube time, we are done. So that's what we have done. We have started with fixing I and j, and we pre-computed the k's. And now after pre-computing k, we saw that okay, this pre-computation itself doesn't take order n square time. Like it takes in order n square time in brute force manner, but we can optimize it by just doing a sort. Now if we are able to optimize this calculate after, then why not try to optimize this order n square loop itself? So calculate after is less than order n square. So if we have to optimize it bit further, we can't iterate over both I and j, and hence we what we tried, we removed one more iteration. We removed I as well from our iteration, and we only fixed j. Now why we fixed j and not I? I think that is clear. We If we fixed I, we can calculate j, but to calculate k, we need to have a j. So in a way, we can't skip over iterating j if we even if we fix I. So that's where we fixed j, and we tried to calculate this I, all the i's for a particular j and all the k's for a particular j, and then multiplied it to get the final output for a single j, right? So hope this makes sense. Now if this is the first time you are seeing this kind of problem, there are multiple problems like this. I would encourage you to code this yourself as well. That would bring much more clarity here. But for now, let's move on to the original problem. That was not the original problem. The original problem states that we have four indexes and we need to find out number of increasing quadruple. And quadruple is defined as these as the quadruples which satisfy these two conditions, right? Now again, order n4 is something, order n to the power 4 is something we are not looking for. We are looking for something which is smaller than that. Now what exactly are we looking for? Let's look at the constraint. Constraint says that n is up to 4000, right? So even order n cube will not pass, because order n cube will be very used than 10 to the power 10. So that will surely not pass. So we are looking for something of the order n square, right? Now can we have can we have login here as well? Order n square login, can it, is it okay to have order and login here as well or not? Is something which is debatable because of given constraint. This may or may not pass, but for now what we surely know is we can't do this in order n cube. We have to do this in order n square or order n square login, right? Now we have to do this in order n square. What does it signify? It signifies that we can only fix two indexes out of these four, right? Now which two you will fix? Now first like, the same argument that we have applied previously applies here as well. So if we fix, let's say this is I and this is j, if we fix these two, we always need to fix k because L depends on k. So if we fix these two, k is something we also need to encounter, and hence the complexity would be order n cube. So you can't fix I j. Let's say you try to fix I and k. So this is a possible choice. You can fix this. Basically, you can say that okay, find me all the indexes j which are in between this I and k, and you can just find all such indexes k, and for L you can find me all the indexes L which are after k. Now notice that this part is exactly similar to what we have solved previously, right? So this part is something we don't need to worry about. Only thing we need to worry about is this particular piece where we have said that okay, find me all the j which lies between I and k, right? So what you are saying is for a single index, you already have two indexes here. Now, if you try to apply brute force, what you will be getting is, first of all, you can't apply uh, sorting very well here. And even if you are applying sorting, you can't, like, you have to have that order log n factor, right? And that is something we don't want in our solution. So basically, if we are fixing I and k, whatever pre-computation we will do, that pre-computation will have to involve I and k both, right? So instead of a single dimension array, we would have two dimension array. And to build this two dimension array, we already require order n square time to build this two dimension array. And now whatever we do inside this is extra. So we can't even iterate over a loop. So we are kind of restricting ourselves with having fixed I and k. Now let's see what else we can fix. We can't fix k and l because of same reason of I and j. So it let's see if we fix j and k. If we fix j and k, this is exactly similar to what we have just solved. So find me all the I which are before j, right? And find me all the k which are before, which are after, find me all the l which are after k. Now these two you can solve, like you can try to solve in exactly same manner, right? So what exactly our pseudocode would look like? Exactly similar to previous one. We will fix j and k. We will calculate before smaller and after greater, right? And we will just multiply them. Now there is a twist here. The twist here is in the previous problem, everything was strictly increasing in the second condition as well. So we don't need to care much about the ordering. But in this particular problem, that's not the case. We do have to care about the ordering of individual elements as well. So in this particular problem, J and K, for J and K, we can easily determine this ordering whether it is true or false because we have already fixed J and K explicitly. For I and L, we we need to now see that, okay, if tell me every indexes I which are less than j. So j is the first dimension, right? And second dimension is all those indexes should be less than nums of k. So that's the second dimension. So we have two dimensions now. Tell me all the indexes before j which are less than nums of k. So they are two dimension, hence this before smaller has now two dimension. Tell me all the indexes which are less than k, which are less than nums of k, and which are less than equals to nums, which are less than equals to j minus 1, right? So this is what we need to solve for now, right? So we will just solve for before smaller and we will see, okay, after greater is exactly similar, right? So now what we are trying to solve for is, okay, first of all, if we are able to solve this in order n square time, our entire complexity would be order n square. I hope that is clear now because we have these two loops only here. So this is order n square. And if we are able to compute this 2 in order n square, overall complexity would be order n square, which will surely pass, right? So now what we need to solve for? We need to solve for given, we need to calculate results ij where result ij would denote how many indexes j, how many indexes are there which are less than equals to j, and the value of those are smaller than array I. That's what we need to, that's what we need to count for. Now in this particular scenario, if let's say this is the I and let's say this is j, right? Sorry. So what we are looking for is how many indexes are there in this range which are smaller than 4. So answer would be 1, right? So hope this what we are trying to calculate is clear. Now how to solve this? So we need to fill this 2D array first of all. For each I, we need to fill a row. For each I, we need to fill a row for j, right? Now let's say this is I. Now why I am fixing I and why I am not fixing j? The reason is simple because I is the one which has the value in it, right? So we need, like, I am fixing I because value remain constant in this while calculating this for different j's, right? So let's look at an example that will make things more clear. So for each I we need to calculate this rows, right? Now what does what does this mean in brute force manner? So in brute force manner we would be doing something like this. So for each I we need to calculate all the j's, right? And for result ij, what result ij we denote, find me all the indexes which are before j, right? So you will just iterate over a k, another index j. Let's say this is j, right? So if this is j, you will just iterate over all the indexes which are before j and just find out how many of them are less than 4, and that will be your answer. So that's what we are doing. We are just iterating over all the k, and if the current element is less than array I, we are incrementing our result. So this entire thing takes order n cube time, but we need to do that in order n square time, right? So how to do this in order n square? First of all, we can't skip iterating over these two indexes I and j for sure. Why? Because we have to fill this entire two-dimension array. So to fill entire two-dimension array, we do need to iterate over every cell at least once, right? So this I and j is something we can't skip. So what we can skip is, or what we can try to skip is this particular piece, this k. Now I would again encourage, pause the video, think about it yourself, and then come back. Now one thing, like one hint that I can give you right now is uh, prefix sum. You can use prefix sum here very easily. Now what exactly will you do? Let In this particular loop, look at this condition. Array I is greater than array k. Now this condition doesn't include j at all. This j was fixed, and it is fixed, like this condition doesn't include j at all. And because that's the case, like k, array k is something which is like which we need to, this k varies with j, right? But this condition doesn't include j. And because that's the case, whatever we have calculated for, let's say, this j would remain true for this j as well, right? Now why that's the case? Because array I itself is constant. So what we are comparing with is constant. And because that's the case, we we can always say that, okay, if we have calculated something for a particular j, we can reuse that for the next j as well. So let's look at that. So let's say we need to fill uh, one part of the array. For one I, we are trying to fill all the j's. So j is 0, 1, 2, and so on, right? Now what we will start with j equals to 0. So let's say this is j initially, right? Now for this j, what we are trying to find, tell me all the indexes which are less than equals to j and which are smaller than array I. So is 6 smaller than 4? Answer is no. So result here would be 0, right? So that is good. Now for 1, do you need to iterate over 6 again? What you will find is, okay, tell me all the indexes which are less than 4. Now, do you need to iterate over 6 again? Answer is no. You can simply reuse this, right? What you can say, okay, I know there are 0 elements before me. So the value of this would be 0 plus whatever decision we have taken for the current element. So what is the decision? Is 1 less than 4? Answer is yes. So we will add 1, and hence this will become 1, right? Now let's say you increment j again. Now for this j, again you have to take these two indexes as well. But for these two indexes, you already know the value, which is 1, right? So you can simply do, okay, I know already there are 1 indexes before me which are less than 4. Now what about 4? Is 4 less than 4? Answer is no. So this will we will add 0 here, and this will become 1. Now similarly, if j is this, you will do the same thing. You know there is one index only in this particular piece, so you will just add one already, and then for this index you all know the contribution will be 0, so this will be 1. And finally for this 2, you know there is one index already before me, and these two also contribute because 2 is less than 4, so you will just add 1 here and this will become 2, right? So hope this is clear now how we are filling it. Instead of iterating over all indexes, we are just reusing them. And why we are able to reuse? Because array I, the thing we are which we are comparing with, is already fixed. So hope this makes sense. Now again, I would try to bring your attention to this ij. I intentionally put I first and j second, or in other words, I am intentionally trying to fill it row wise instead of column wise. Because if you fill column wise, this will not be true. You can try filling column wise and you will see, okay, this loop will contain all three variables I, j, and k. Like this condition would be bit complex, and because of that, here applying that would not be that easier. So that's where we have fixed I, because now what we are comparing with is fixed. So this loop is something, this condition is something which we are trying to reuse every time and try to skip iterating over all the already calculated indexes, right? So hope this makes sense. And the final code would look something like this. Like you will have this as a uh, starter code, and for this calculated before, calculate after, you will apply these two index, like these two loop, and inside this two loop you will just do the exact thing that we have done here, right? So again, that's the entire solution. This entire thing runs in order n square, and this entire thing already runs in order n square. So hence, the overall complexity is order n square. I haven't shown calculated after uh, knowingly, so that you can try it yourself. Now, the very important part, if you have watched till this part of the video, I really appreciate you. Uh, and if you have put this much effort, I would encourage you to put an extra effort and try to code this entire thing yourself and try to get that submitted. The exact pseudocode is something we have already discussed. We have already discussed a small example as well. We have did a dry run for a particular INJ, and I would encourage you to rewatch that particular piece if you have any difficulty while implementing. And I would strongly encourage you to code it yourself, because this has lot of things that you will get after coding it yourself. Calculate after would not be exactly similar to calculate before. There will be small difference, very small difference, in which you will be finding out calculate after. So if you code it yourself, that all things you will be able to absorb much in a much better way. So next section we will look at what I have implemented. But as I would encourage you to pause the video and code it yourself. Still here, if you haven't tried it yourself, just try it right now. So let's look at the code. The code is before, like, first of all, this is exactly similar to our driver code that we have saw. We are fixing j and k, and then we are checking the conditions with j and k satisfied or not. If they are not, we will continue. So we want nums of j should be greater than nums of k, right? Nums of j should be greater than nums of k, and if it is not, we will continue, right? Otherwise, we will just find out before smaller of k j minus 1 and after greater of k j k plus 1. And how to calculate this? Let's look at the before function once. So result ij, as we discussed, we will say how many indexes that are there before j which are less than array I, right? So this is this you can ignore, like this is I put for implementation purpose. So here what we are doing, we are just iterating over I and j, right? Now we are starting from 0, and we see which, so let's say we are index j, some j equals to 2. So at j equals to 2, we will know that, okay, we have to find everything up to 2. So we know what is there up till 1 is stored in result of I and j minus 1. So we'll just initialize this with result of I of j minus 1, and then just see what is the status with the current element. Current element is j, so we'll see if j is greater than if j is less than array I, then it will increment the result, otherwise it will not. So hope this makes sense. So this entire thing would run in order n square, and result ij would contain finally how many indexes are there which are less than, which whose value are less than array I and whose indexes are less than j. Now the same way you will calculate after as well. I am intentionally not showing it right now so that you can try it yourself. So that's all. That's all about this problem. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.